Okay. In the context of cold fusion, that is we really do not know what goes on inside it, but there are some possibilities that this excess heat can be understood by some kind of that deuterium atoms can tunnel. It's called quantum mechanical tunneling that the quantum mechanics allows, and that I will elaborate a little more in this talk. And they say that it gives very interesting results for a theoretical possibility that cold fusion should exist, because people have dismissed this because there is no theoretical mechanism behind these basic principles of physics to understand cold fusion. Okay, because the Coulomb barrier is really a big barrier. Okay, coming back to the quantum mechanics here, so how this barrier can be overcome? In classical mechanics, a particle with less energy than a barrier height cannot go to the other side, you know it. But in quantum mechanics, permits this due to the tunneling effect, as a particle has also wave nature. Because the particle has a wave nature, so certain principles allows this. Okay, you can see a picture. Classical mechanics, electrons, they can only climb the hill, climb the upward and go to the downward. But in quantum mechanics, they can tunnel through. This is a kind of cartoon. The balls can go to the other side because they have a wave nature of particles allows such things to happen. And one can see here quantum tunneling through a barrier. So even if a particle's energy is less than the potential barrier, and it can still tunnel through the barrier and go to the other side, but with some probability. It's called quantum mechanical tunneling. Okay. Now the existence of electrons is in the deuterium atoms in relativistic quantum mechanics has renewed interest. So earlier there was no possibility of electron coming very close to the nuclear dimensions, but later it has been known that if you solve quantum field theory models of Dirac equations, there are some solutions. They allow deep electron orbits. Those orbits are stable, but probability may be low. So the deep electron orbits, the deuteriums, for the electron, they can come closer to each other and they can come very close to nuclear dimensions, and that can facilitate the fusion and quantum tunneling hand-in-hand fusion. So that is the consequence of later development of relativistic quantum mechanics. I will not get into detail those things. Time is short. So there is a concept called vacuum polarization. Here. There is something you see. There is something called vacuum polarization in quantum field theory. That vacuum is not empty. A vacuum is filled with so there is energy. That energy can split into particles and antiparticles. They can recombine from energy. This process goes on. This is called vacuum polarizations. This is called effect of vacuum. So these virtual particles can interact with other particles, including deuterium nuclei, and affect their behavior in various physical processes. Right? And actually when this let's say electron positron pair is created from vacuum, and they can stay for a short while and they can annihilate again, and as such then the electrons will be attracted to the positive nucleus, so they create a kind of screening effects for the effective Coulomb potential. They have a power to reduce the Coulomb potential. So the purpose of this talk is to use that mechanism and show that tunneling probability can be enhanced by the screening effect due to vacuum polarizations. One example is here. There's a Feynman diagram. A photon comes on the left side, gamma, and it splits into electron-positron pairs that is allowed particle-antiparticle. Again, they recombine and become a photon. But this is a Feynman diagram process in quantum field theory that allows such a process to go on. So there are different kind of higher order Feynman diagrams, but this is the simplest one diagram. If you incorporate, it will give an interesting results. The virtual electron-positron pairs that are created and annihilated, they can modify the Coulomb potential experienced by the deuterium nuclei. That makes it easier to tunnel them to the barrier. The barrier height will be reduced, and they will reduce the height and width of the Coulomb barrier, thereby increasing the tunneling probability. Also, the electron-positron pairs, they interact with the deuterium nuclei and modify their energy levels. This can have the effect of shifting the energy levels of the deuterium nuclei closer to the top of the Coulomb barrier, making it easier for them to tunnel through the barrier. There is something called self-energy, that means that due to this mechanism, the energy of the deuterium nuclei can be increased, and that can also facilitate tunneling. To calculate the effect of polarization on a particular process, one can include the appropriate Feynman diagrams in perturbative expansion of quantum field theory. Okay. So the effect of polarization calculated in perturbation theory, there are some technical. This is the involved lot of mathematical jargon, very complex mathematical calculations, all those things. And it is such a successful theory that it is verified with very high accuracy in elementary particle experiments like the lamp shift and the magnetic moment of electron and so on. So these are already well established theory. So the vacuum polarization energy can be expressed as sum over all possible Feynman diagrams that describes the interaction between virtual particles and the deuterium nuclei. So then one can then use this calculation to determine the tunneling probability of the deuterium nuclei. So this involves solving the Schrödinger equation for the deuterium nuclei, taking into account the potential energy function and the effects of vacuum polarization. Because Schrödinger equation is very common in quantum mechanics. It involves a energy function and a potential function. But this potential energy can be modified here by taking into account vacuum polarization, and it will be somewhat reduced, and that can be applied to Schrödinger equations with the boundary conditions to find the tunneling probability, what was before and what was after. The expression for the tunneling of deuterium nuclei can be calculated using that approximation called semi-particle approximation. These are too much mathematical, these topics, slightly maybe different from what other people have been speaking. These equations. So the WKB method is a semi-particle approximation. We calculate the probability of tunneling to a potential barrier. So that can be given as exponential of minus twice over g, the gamma factor, and that is given by particular kind of form that has been found different kind of analysis for which I cannot go here. Those who are experts, they can know this. So these are called charges of the colliding nuclei. This is the elementary charge, m is the reduced mass, and total energy of the particle. So this formula will be used to calculate things. So if this is E and U are there, so the energy can be modified by vacuum polarization, and potential energy function can be verified, and we can use those vectors. So expression for Coulomb barrier is given by Z1 Z2 E square by 4 pi epsilon 0 r. This is the standard Coulomb equation for Coulomb barrier, and that is the kind of repulsion, the two nuclei that we for each other, epsilon 0 permittivity of this way. So the expression for the tunneling probability of deuterium nuclei, the Coulomb potential barrier, can be used to calculate the probability for various fusion reactions. They have a lot of use in astrophysics, nuclear astrophysics, and experimental nuclear physics. Okay, the screening effect of the refers to the reduction in effective barrier height due to the presence of virtual electron-positron pairs created by vacuum polarization. So you imagine there are two positive nucleuses, and in between them, the electron-positron pairs, they are like clouds, they are hovering. So what happens? The electrons will be attracted to the positive side of this nucleus. So they are reducing the screening effect.
You have only 2 minutes. Please go to the conclusion as soon as possible.
I have only 2 minutes?
Yeah.
Okay, fine. Then I will skip all those things. There is a polarization potential can be found like this. Then self-energy correction can be calculated like this. Then a solution can be written as a, okay, this is a quantum tunneling, short distances that can happen. Summary. Okay, I will finish in as you said, within 2 minutes. Okay, I come to the last one. For a deuterium nuclei separated by a distance of order of 1 femtometer, 10 to the power minus 15 meter, the Coulomb potential barrier is about 14.4 MeV, but the energy is about 100 keV. range, kilo electron volt energy of the nucleus. So in 1 book per example of cell energy, which is Feynman diagram, the effect on the energy of the plutonium nuclei was insignificant because in cell energy calculation it didn't contribute much. But in vacuum polarization, it contributed very significantly to the screening effect, reducing the height of the potential barrier. And finally, this quantum mechanical tolerance probability increased significantly to allow deuterium nuclei to fuse. So the two methods were used, WKB methods and another is called barrier penetration method using Schrodinger equations. Both of them showed significant increment of energy. So at extremely short distances, nuclear force which is attractive and X over very short range overcomes the electricity repulsion between positively charged protons in the nuclei. This allows the nuclei to get close for the attractive strong nuclear force to dominate, leading to the fusion process. What happens? There is there is some problem, extra things came up. So my last slide, the detailed mathematical and numerical calculations will be presented in another paper. But now we are strongly working in new direction to take into account the multiple contributions of Feynman diagrams, the quantum perturbative theory of quantum field theory for the vacuum polarization on the tunneling probability. So we are hoping that it will use these higher order corrections. They are like Taylor's in higher order terms. They may further improve its tunneling probability. So it provides a very solid theoretical mechanism why cold fusion should exist in nature. There is no law in physics that forbids it. So that is the strong point of this talk. That there is a theoretical mechanism supports this existence. Okay, thank you so much for your kind attention.
Okay, thank you. One more person? Okay.
Yeah. One quick question. I could have this wrong, but in order for the initial assumption that these virtual particles can actually affect the tunneling probability, wouldn't that require something on the order of electron rest mass energy to realize those particles? And where would that energy? I mean, I think you said something about it would come from the last. That's quite a bit of energy. How would you have that much concentrated energy in a local field in a condensed matter phase to realize those virtual particles, those real particles, which could affect the tunneling barrier?
Okay, yes.
Now, that is fine, but that is a fundamental feature of our vacuum. See, in our quantum theory, vacuum is not empty. Vacuum is very active with all these things. It's called quantum fluctuations. They are going on all the time. So this is a very important discovery in modern physics that every time the virtual particles keeps coming and going, and then depending on the system, they have a tremendous effect on other elementary particle studies. For example, if you calculate magnetic moment of an electron in quantum or quantum electrodynamics in math, they use all these calculations and they agree very high accuracy with the experimental data. So they have a role. So we are believing they have a role here also implement the condensed matter, but still the processes are very much fundamental and very much universal in nature. So they provide a strong ground to consider them to study the screening effect of these virtual layers.
Maybe I will reach out over email or something and we can discuss further. Thank you.